now call to order the Society's 2,407th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Mariangela Lisanti in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a few announcements and a reading of the minutes of the 2,406th meeting and the lecture by Dagmar de Groot on A Frigid Flowering, the Dutch Republic in the Little Ice Age. We will then turn to this evening's lecture, followed by a question and answer period, and thereafter I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me first in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who was asked to remain anonymous. Please also join me in thanking the sponsor of tonight's lecture, PSW member, physicist, and software engineer, Erica Kane. Erica. She is CEO of CenturyLink, and she's here tonight with her family, including her two lovely daughters. Thank you, Erica. I'm pleased to announce that the following new members have been elected to the Society. Zakaria Shako, professor of physics at the University of Maryland, interested in elementary particle physics, who comes to PSW through PSW speaker member Raman Sundram. Victor Vaughn, an engineer interested in bioengineering and modeling natural phenomena, who comes to PSW through the NOVA section of the IEEE, which has expressed a special interest to, as they put it, emulate PSW's live streaming and video archiving. Thank you for the compliment. Thomas Francie, retired from Wells Fargo, teaching at NOVA, interested in quantum physics and cosmology, who learned of PSW from the Washington Post. Elizabeth Thomas, an expert in international trade at the U.S. Export-Import Bank, interested in astronomy, robotics, and telemedicine, who also learned of PSW from the Washington Post. Robert Ryan, a meteorologist, interested in meteorology and climate science, and in physics, especially astronomy. Derek Oates, a cybersecurity engineer, interested in green energy, physics, especially the LHC and gravitational waves, astronomy, and AI. And Frederica Derima, director of the Air Force Office of Scientific Research, a former PSW speaker. She is interested in mathematics, computer science, and nuclear physics, and their interaction with other fields, especially aerospace and materials sciences, nanotechnology, and supercomputing. And tonight's speaker, Mariangela Lisanti, whose background and interests will be clear to you in part from tonight's proceedings. Please join me in welcoming them to the Society. All our new members receive a copy of the first volume of the Bulletin of the Philosophical Society of Washington, as it was originally called, when it was founded in 1871. Least importantly, signed by me. More importantly, it has the original members and the address that explains why the society was founded, what the founders hoped to achieve, and why they called it the Philosophical Society. So if you're a new member, either announced tonight or previously announced, and you haven't picked up your copy, please do. I should also mention that all new members are entitled to wear the rosette of the society, and if you haven't purchased one, you may do so as a member in good standing at the rosette table in the back during the social hour. I'm sorry that our recording secretary, James Heelan, cannot be with us tonight, but he was kind enough to send me the minutes of the 2406 meeting and the lecture by Dagmar de Groot on a frigid flowering, the Dutch Republic and the Little Ice Ages, cultural adaptation to climate change, which was delivered here at the Cosmos Club on March 22, 2009. And I will read them to you on his behalf, but I did not write them. On March 22, 2019, in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the 2406th meeting of the Society to order at 8:02 p.m. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. President Milstein then introduced the speaker for the evening, Dagmar de Groot, Assistant Professor of Environmental History at Georgetown University. His lecture was titled Climate Change and Cultural Adaptation, A Frigid Golden Age. For a century, paleoclimatologists have scoured the globe for proxy sources of evidence of prehistoric climate change, and have focused in particular on ice cores and tree rings. Ice core particulates provide evidence of geological events, and their ratio of oxygen to hydrogen isotopes are evidence of temperature across the ages. So using such proxy sources, he said, scientists have reconstructed the temperatures at various points around the globe. He particularly pointed out the most recent 1,000 years of reconstructed climate data, showing that periods of warming and cooling affected different parts of the globe at different times. Overall, the data shows, he said, anthropogenic global warming with a period of global climatic cooling from approximately 1350 to 1800 CE. This cooling period is called the Little Ice Age and includes 3 distinct temperature fluctuations. Historians focusing on the Little Ice Age have recently argued, according to de Groot, that climatic cooling influenced patterns of atmospheric circulation and brought precipitation extremes from one region to another. These changes interrupted growing seasons, leading to harvest failures and food shortages. Malnourishment led to disease epidemics, and violent conflict followed. According to one historian, he said, there were more revolts and rebellions in the 1600s than ever before or ever after. Working with scientists, de Groot reconstructed the climate history for the area that we now know as the Netherlands. He concluded that the climate during the period of the Dutch Republic grew colder and stormier, with each of the Little Ice Age's 3 successive cold waves. Commercial records from the period of the 3 cold waves show the Dutch Republic was at risk of economic collapse. But, he said, climate change created positive impacts that allowed the Dutch to persevere. For example, he pointed out that a high and low pressure zone called the North Atlantic Oscillation fluctuates in periods of climatic cooling. In practical effect, he said, cooling produces more easterly winds in the North Atlantic. The groups said that cooling benefited the Dutch in the Anglo-Dutch wars of the 1600s. He said the second and third wars occurred during cooling waves, causing easterly winds that propelled the Dutch Navy to significantly more victories than the English because it favored their lines of ship. These victories saved the Dutch Republic from extinction and allowed it to become a global naval power. The Dutch also adapted to climate changes in other ways. They built ice wagons that allowed them to speed commercial products along frozen waterways. They built icebreakers to open waterways and sold the resulting ice blocks. In response to severe storms that caused urban fires across Europe, the Dutch invented firefighting equipment that they then marketed across the continent. Dutch culture also adapted, creating festivals, winter markets, and winter sports. The Dutch were also resilient, connecting population centers by redundant networks of canals and roads. They ate a diverse diet that minimized the impact of any one kind of weather. Cities maintained civic charity, which de Groot said insulated the urban poor from the food shortages that impacted other European populations during the same period. Last, the Dutch were optimistic. The Republic fed itself through the Moording or mother of all trades, in which Dutch merchants purchased bulk commodities in the Baltic Sea in exchange for low-volume, high-value goods from Southern Europe. They then stockpiled grain in good times and sold it for high prices to other populations when the weather turned ill. De Groot concluded by noting that while the story of the Dutch Republic is instructive, there are limits to society's ability to withstand extreme climate change. He then took questions from the audience. One member asked about the Little Ice Age's effect on the Dutch Republic's political influence. De Groot answered, "The Dutch invasion of England and the Glorious Revolution of 1688 may have succeeded due to the strong easterly winds caused by climatic cooling." Another member asked about the effect of the Little Ice Age on the North Pacific. De Groot said a recent study found a correlation between the speed of the Little Ice Age and the rate of success of Western European journeys to East Asia. A live stream viewer asked about the consequence of deaths of indigenous peoples in the Little Ice Age. De Groot responded that a recent study asserts that depopulation of indigenous peoples in the Americas beginning in 1492 allowed tropical forests to bloom and absorb carbon dioxide from the atmosphere. This period overlaps with the first cooling wave of the Little Ice Age. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:51 p.m., President Milstein adjourned the meeting to the social hour. Temperature, 7 degrees centigrade. Weather, partly cloudy. Attendance in the Powell Auditorium, 84. Viewing through the live stream on the PSW Science YouTube channel, 27. Respectfully submitted, James Heelan, Recording Secretary. Are there any comments or corrections to the minutes? Hearing none, I will entertain a motion from a member to accept the minutes as read. I have a second. All members in favor? Aye. All members opposed? The minutes are unanimously accepted as read and will be posted to the website in due course. So we now turn to what everybody's been waiting for, the lecture on understanding dark matter, archaeology of the Milky Way, the mystery of invisible mass. It is my pleasure to introduce tonight's speaker, Mariangela Lisanti. Mariangela is a theoretical physicist and assistant professor of physics at Princeton University. She is primarily interested in dark matter, which, although it comprises nearly 85% of the matter in the universe, has so far eluded direct detection, and its fundamental nature remains unknown. Mariangela's research focuses on understanding the particle and astrophysical nature of dark matter through its detectable signatures. She tests ideas about dark matter using data from a wide range of observational probes, including gamma ray and astrometry missions. Mariangela is an author on numerous scientific publications, and among other honors, she is the recipient of a Sloan Research Fellowship and a Cottrell Scholar Award. And she was a finalist for the Blavatnik Award for Young Scientists. She earned her BA at Harvard and her PhD at Stanford. Please hold questions for the question and answer period at the end of the lecture, And join me in welcoming her to the podium.
Whoa, that was very loud. That should have woken you all up. First off, I want to thank you for the honor of being able to talk to you all tonight. It's a wonderful pleasure to be down in DC in this amazing space. And I'm very excited to spend the next hour telling you a little bit about dark matter, which is mostly going to be a story of everything that we don't know. To start off with, I'm showing here a picture. Let me get here we go. So a picture of the Milky Way as seen from New Zealand. I wish I was a good enough photographer to have been able to take this kind of image, but I find it really inspiring to look at pictures like this. I feel like we're confronted with the vastness of what's out there when we look at images like this. And this also is going to set the theme for our conversation over the next hour, because what we're going to be doing is trying to understand how we can take all of this information of what we can actually see in our galaxy, so all of these stars that are forming this amazing structure here, and how we can use that to find out and learn something specific about everything else that's out there that remains dark to us and that we can't actually see. So before we get into the meat of the talk, I want to do a little bit of a warm-up. So you might have noticed when you sat down in your chair that there was a sheet that had 4 different colors on it. So if you can fish that out. At various points over the course of the talk, I'm going to want to just kind of get your reading on what's going on. So I will ask a question, and what you will do is fold the sheet of paper to the color. It'll be a multiple choice question. So you'll fold the sheet of paper to the color, that's your answer, and then hold it up. And then I'm going to do a kind of non-scientific tallying of results based on the colors, and we'll see what the audience opinion is. So as a warm-up, let's just start with an easy question. So you know a little bit about me. I'd like to know a little bit about you. Are you a DC native? Are you from out of state, out of country, or out of galaxy? So pick your color and then hold it up. Let's see what we got. Interesting. Okay, so vast majority is actually out of state. We had a couple aliens. The rest are from DC. So this is good, because actually the aliens can probably answer our questions about dark matter. So we'll be coming back to you later. Okay, so keep those handy, because there'll be various points where we'll be using those again. Okay, so here's going to be roughly what we're going to talk about over the next hour. I'm going to start off by just kind of introducing the idea of how we can use gravity to learn something about matter, and in particular about the missing matter that we believe is out there in the universe. Then, with that backdrop, we're going to talk about how we can actually build experiments to look for this dark matter so that we can actually test it and study it in the lab. And one of the points that I want to make there is that we can't, a critical element of that is going to be the fact that we actually need a map of where the dark matter is in the galaxy in order to be able to do that. And so in the last part of the talk, I will describe to you how we can actually build that map. But let's start off now with the topic of gravity and how we can use gravity to learn something about matter. Now, we're going to be talking about how we use it to learn about dark matter, which is exotic. But in some sense, this idea has a very humble origin in some sense. It's actually how we discovered Neptune back in over a century ago. So what was noted at the time was that there were perturbations in the orbit of Uranus that were inconsistent with Newtonian gravity predictions for Uranus's orbit. And one potential explanation of this was that there was some other planet that we hadn't seen before, whose presence was actually perturbing the orbit, and so a hypothesis was made that Neptune should exist based off of its gravitational effect on Uranus. And indeed, after this prediction was made, Neptune was discovered. So this is kind of a really wonderful example of how we can use information about, you can use gravitational effects of things we can't see to infer its presence. And what we want to do now is essentially extrapolate this kind of lesson to scales that are a lot larger than just our own solar system. So let's zoom out from this picture and consider the rotation of our galaxy. All right, so our own solar system, so the picture I showed you on the previous slide, is essentially out, about 30,000 light years from the center of the galaxy. So we're in a tiny little neighborhood. Essentially, we're in the suburbs of the Milky Way. We're not near the center. We're not near the metropolis where all the super exciting things are happening. We're just kind of here on the outskirts hanging out. So here's the sun. Like I said, about 30,000 light years from the center, and it's orbiting around the center of the galaxy at a kind of a whopping 440,000 miles per hour, so super fast, right? What we want to do is ask, well, we can make some prediction about how fast the sun should be moving based off of the amount of matter that we see inside its orbit, using just Newtonian gravity, and we want to see if that's consistent. So again, kind of applying the same philosophy that had been used in studying Uranus's orbit, we now want to do that with just stars orbiting around the center of the Milky Way. So a little refresher course in Newtonian gravity. So in Newton's theory, essentially says that the speed of any star or planet is going to be set by the mass of the stuff that's enclosed inside that orbit. So that speed of that object is going to decrease if this mass decreases, or if the distance to that mass increases. So there's two effects kind of going on here. So given this, let's consider what happens if we have two stars now orbiting around the center of the Milky Way, so star A and star B, where star B is located sort of further out near the outskirts. And I have a question for you. So given A and B and your intuition from Newtonian gravity, which of these two stars is, which of the following statements is true? So is star A moving faster? Do you expect star B to be moving faster? A and B to orbit at the same speed? Or really, I'm just kind of bothering and you really want to go back to sleep. So great, yeah. So we have mostly star A moving faster, some star B's moving faster. It is a little bit of a trick question because you do need to know something about precisely how the the visible mass is distributed in the disk. It does turn out that mass is kind of concentrated near the center here. So indeed, actually, star A is moving faster in this case. So for the Newtonian scenario, if we were to plot the rotation speed of the stars as a function of distance from the center of the galaxy, we'd expect, given how much mass we can visibly see, that star A has a higher rotation speed, it's moving faster, than star B. Awesome. This is what Newton would have said would have happened. This is great. We have our prediction. Trouble is, you go out and you do the measurement, and this totally fails. So this is what we actually see. What we find is that as you move towards the outskirts of the galaxy, everything is sort of moving faster than you would otherwise expect from Newtonian gravity. Right? Now, this is Newtonian gravity, right? This is a tome. This is what we teach in high school physics. This has, been around for many hundreds of centuries. The fact that what we are measuring is in contradiction to that Newtonian prediction is, to say it mildly, a huge issue that we need to contend with. And indeed, one of the pioneers of this work, so this was really, these ideas and these measurements were really developed by Vera Rubin in the 1970s and early 1980s, so this is fairly young work. There's Before I actually go to a quote from Vera Rubin, I did just want to show you visually what this actually ends up looking like with this movie. So this is what you'd expect from Newtonian gravity in terms of the rotation of the galaxy, and this is what we actually see. So in particular, you see that the main difference is that the outskirts of that galaxy are rotating a lot faster than you would otherwise expect from Newtonian theory. So there's this famous quote from Vera Rubin, who was crucial in demonstrating this, where she says, "I don't know if we have dark matter or we have to nudge Newton's laws or what. I'm sorry I know so little. I'm sorry we all know so little, but that's kind of the fun, isn't it?" And that's going to essentially set the tone for the rest of the talk. So there really are, as indicated in this quote here, two possible explanations for what's going on. The first is we say, well, we have to throw out Newton's laws of gravity. Like, they're failing. We need a new theory of gravitation. And the second is, well, maybe Newton's laws are still correct, but there's actually a lot more mass there that we cannot see. And so what we have to do as scientists is figure out which of these two possibilities is the likely one. And our primary way of doing that is, again, to go back to the data and see what the data tells us. Oops, wrong direction. There we go. So the modified gravity hypotheses, there's a variety of different kinds of phenomenological models that have been written down. They tend to have numerous challenges to them, so there isn't one that sort of has gained a lot of traction. I think perhaps one of the easiest to understand issues with modifying gravity to explain this anomaly is the following one. So what we see with these rotation curve measurements, the fact that stars on the outskirts of the galaxy are orbiting faster than we would otherwise expect, is essentially a statement that their acceleration is larger. What we observe their acceleration to be is larger than what the theory predicts, Newton's laws of gravity predict. And so if you're going to modify Newton's laws of gravity, what you need to do is essentially enhance accelerations, make them faster. If you do that, you not only end up enhancing accelerations towards the center of the galaxy, you also end up enhancing accelerations off the plane of the galaxy in this direction. And so that's something we can go out and test because we have lots of data on stars in the disk. We can look at their motions in and out of the disk, and we can see whether or not their motions are consistent, that vertical motion is consistent with Newtonian gravity or not. And it turns out, when you look at that it's actually quite consistent with Newtonian gravity. So that means that this provides a really strong constraint on any modification you're going to make to Newtonian gravity, because the motion of the stars in this direction is consistent with the Newtonian prediction. So that makes it really hard to find a way in which you'd modify that gravitational picture to be able to explain our observation of the rotations. And so what we're left with then is the hypothesis that maybe there's just a lot more stuff there than we can't actually see. So what is this stuff, and where is it, and how would it be distributed? Well, the picture that we have is in mind, again, this is all a hypothesis, is that there's essentially some halo of this stuff, we'll call it dark matter just because we have no better name for it, that's surrounding the visible part of the galaxy. But sizes here are really important, and I didn't even draw this exactly to scale because this is probably too large as drawn. So the amount of dark matter that's surrounding our visible galaxy is huge. And essentially the visible part of the galaxy, everything that we spent centuries studying, is a tiny little speck that's there. And so we're just surrounded by this massive, massive amount of halo that's there. The first ideas and theories about this were put forward in the 1970s and 1980s, and a lot of those ideas are still kind of adopted in the field. And so, when you start off with a hypothesis like this, you always kind of use the simplest kinds of assumptions. So, we know that we expect that this halo is going to extend about 10 times as far out as the actual disk. So that's what I was telling you, it's really, really big. We assume for this super simple model that the dark matter is smoothly distributed, so it has no structure really, it's just, you can think of it almost as like a gas that's kind of surrounding us. The actual motions of the dark matter in this gas are really slow. I know a lot of people ordinarily ask me like, oh, if it's dark matter, it's something exotic, it must be moving at relativistic speeds, and I wish. Like, it's not, it's actually just moving at essentially the speed of the sun, so 440,000 miles per hour. Like, it's pretty slow for astronomical scales. And additionally, we assume that the dark matter is kind of moving and it has no preferred direction. So really, this picture of a gas cloud is not too far off. And you might ask, well, why is the dark matter in this big spherical halo and everything we can see is in a flat disk? That seems like the geometries there are different. And the reason for that is we're assuming that whatever this novel particle is, it's not interacting very much. And we're assuming that because we haven't seen it. And so if it doesn't interact very much, that means it doesn't lose energy the way atoms lose energy. So when we have atoms, they can cool. When they cool, they collapse to form disks. So that's how we get this disk here. But the dark matter, if it can't cool, then it just kind of stays as a big halo, kind of big spherical distribution. So that's why the geometries of the two components would be different in this picture. So how does this affect you and me, right? Well, we're, at the sun's location. We're whizzing around the center of the Milky Way. We're essentially flying through this halo, and we're flying through it right now. So billions of these dark matter particles are actually, they're in this room, and they're flying through your body at this very moment. It's just we don't notice because they're so very weakly interacting. So just to kind of see how many you think might be interesting in terms of hitting a nucleus in your body, if you get ready with your cards again, do you think that in the course of a year, remember there's about 1 billion of these that will have gone through your body in the course of a year, how many of them will have actually hit a nucleus in your body? Is it none? About 10 to 100, a few million, or essentially all of them? Interesting. So it's actually almost uniformly distributed amongst all colors. So it turns out that for very weakly interacting dark matter particles, the number is about 10 to 100. So it's not none, but it's pretty close to none, right? Considering how many have actually flown through your body by that point in time. And so while that may seem like it's some very rare event that would occur, the fact that any have the possibility of potentially even hitting a nucleus in your body, as physicists, gives us hope. Because that means that maybe we can actually replace your body with a really sensitive detector, and then have that detector pick out the 10 or so dark matter particles that fly through it and actually hit a nucleus in the detector. And so that's going to lead me to the second part of the talk, which is how does this happen, and what kind of detectors would we build to actually look for these kinds of interactions? So what we need is something, like I said, that needs to be really sensitive because these collisions are going to be so incredibly rare. So indeed, most of the other kinds of processes like cosmic rays or things like that that can also lead to these types of signatures would far dominate the dark matter signal. So you have to put these experiments like deep underground in mines or deep at the bottom of mountains where you can shield out all possible backgrounds. So you essentially want them in these kind of ultra quiet, low noise environments. So you build your tank. In this case, this is a picture from an image of from one of these experiments that is using liquid xenon. You build this big tank. Essentially, think of it as a tank of nuclei. And then you put this tank in some really quiet environment. In this case, they have this experiment is under a mountain in Italy. And you wait. And you just keep waiting, right? Because what you're waiting for is hopefully some dark matter particle from our, the halo that's surrounding our galaxy is going to fly in. It will hit the nucleus, and when it hits the nucleus, it'll cause that nucleus to move, and you might be able to actually detect the motion of that nucleus as it moves. So that's the hope for what you might actually be able to see in one of these experiments. And there's a whole variety of these types of experiments that have been built and have been deployed around the world. So this is a vast program right now that's trying to detect dark matter on Earth using this kind of methodology. So at the sort of most fundamental level, what's actually happening when the dark matter particle comes in and sees the nucleus? One way it can interact with the nucleus is through the Higgs boson. You might have the Higgs boson is maybe one of the more popular of our particle physics particles. It was discovered only a few years ago at the Large Hadron Collider. It's the particle that's known as giving mass to all of the other particles that exists. And one potential way that the dark matter particle can talk to the nucleus is if it comes in and it exchanges a Higgs boson with the quarks that are inside the nucleus, and then it recoils off. So in some senses, the Higgs is almost acting like a Wi-Fi signal. So dark matter particle comes in, sends its little like Wi-Fi or maybe a little email message through its Wi-Fi, and the Wi-Fi is essentially the Higgs, sees that there's a quark there, and then the signal that comes back is that it's going to just bounce right back off. But the only way that dark matter particle is actually seeing that nucleus is essentially through this Higgs boson for this particular example. So the actual details of this collision and what you expect to observe really just kind of boils down to billiard ball scattering. So if you've played pool, you have all of the intuition that you need in order to understand what happens when a dark matter particle comes in and hits a nucleus. So this is just an image of before the collision here, and this is after. Remember that in this process, we never see the dark matter particle. That's always invisible to us. And so the only thing we have any handle on is the nucleus. So initially, before this collision, the nucleus would be sitting at rest. And then after the collision, you as the experimentalist would see the nucleus recoiling off. So what you're looking for in these kinds of experiments is just that nucleus after it's gotten a kick and it's moving. You can never end up seeing the dark matter directly. It's always indirectly through its effects on the nucleus. What this actually looks like, let's say this is a simulation within the xenon detectors. You have your dark matter particle comes in, it hits the nucleus, and when the nucleus recoils, it actually causes a bunch of scintillation light inside the xenon, and you would see this as a bunch of scintillation light in your detector. And then, of course, you need like very sensitive photomultipliers that can actually collect all of this scintillation light, and that's how you would analyze that data, and you would try to figure out whether or not the signal that you see is consistent with a dark matter particle coming in and hitting. So there's a variety of ways in which the detection rate in this case would change depending on properties of the dark matter. So of course, it depends on how the dark matter talks with the nucleus. So for this particular example, I'm saying it talks via the Higgs. It also will depend on just how much dark matter there is, right? So if I have more dark matter particles, that means that there's a greater chance that one of them will hit a nucleus in my detector, and I'll see a signal. So that's one way I can increase my signal. The other way is if the dark matter happens to be moving pretty fast, then when it hits the nucleus, it'll impart a larger kick. And so you tend to see that'll translate into a higher rate because you can detect those events more easily. So that suggests then that we need to come back to our picture of the dark matter in the halo because how that dark matter is distributed, what its density is near the sun, and how fast it's moving is going to be really important in terms of determining what we're actually going to see inside these detectors. And so to do that then, we actually need to take this simple picture that we started off with and actually turn this into a much more realistic map of how the dark matter is distributed in our galaxy. And that's going to be the subject for the last part of the talk. And it's the last year or so, and also I think moving into the future, given the data that we've been getting from the Gaia satellite, it's a particularly opportune time to revisit this because we finally actually have enough information to really start building some sophisticated maps of the dark matter in our halo. So one of the reasons why I really am fascinated by this question is because it takes something that's happening at the most microscopic of levels, sort of fundamental particle interaction in an experiment that we've built that's deep underground, and it's going to link it to something that's happening on such larger scales. And in particular, it's going to link it with the history of our Milky Way galaxy. So the idea that I want to try to explain is the fact that we need to understand the history of our Milky Way, how it grew, how it developed, in order to be able to create this dark matter map and then make more sophisticated predictions for our experiments. So again, there's sort of this link on scales that are very, very different in size. So what I want to show you next is a simulation of a galaxy that's similar in nature to our own galaxy, the Milky Way, and I want to show you how it grows. So what this simulation does is it traces all of the stars and all of the gas and all of the dark matter, starting from a very, very early point in time, and then it will demonstrate how the galaxy actually forms. So one of the things that you'll notice once I start playing the video is that the galaxy is forming by all of these smaller galaxies that come in and get disrupted and donate all of their stuff to the host. So let me start getting this running. The galaxy that's going to form is going to be here in the center. You see these clumps that fly in. Each one of those is another smaller galaxy. So essentially, one of these small galaxies is flying around. It gets caught by the gravitational pull of the host here in the center. And then when it gets caught by the gravitational pull, it has no choice. It gets dragged in. As it gets dragged in, the gravity is just kind of tearing it apart to shreds. And all of its stars and all of its dark matter just kind of get eaten up by that host galaxy. So I'll play the movie again so that you can get a sense of that. Again, see that it's starting from hardly anything, and pretty much all of its stars are just coming from these mergers that are occurring, donating all of their components. So it's this violent process where our galaxy has essentially eaten up a bunch of smaller galaxies to get to the point of where we're at today. So we have evidence that we're in the middle of this process today, right? So if we make a survey of all of the galaxies that are around our Milky Way, we see these tiny little small galaxies flying around. So here's, in this map, here's the Milky Way, and here's Andromeda. So Andromeda is going to be our largest neighbor. And then you kind of have to squint, but each one of these tiny little speckles here are tiny little dwarf galaxies that are, some of them are a little bit further away, but other ones are essentially caught. They've already started getting caught by the gravitational pull of the Milky Way, but they haven't reached a point yet, because we're just seeing it today. They haven't gotten pulled in and totally disrupted because they're still surviving. We still see them, right? But this is the picture of what our galaxy is today and what all of its neighbors are like today. What we need to do is run the clock backwards and actually essentially do a little bit of a mystery hunt to figure out which of the galaxies, what galaxies were eaten up and which ones weren't. Essentially, what we want is a family tree for the Milky Way. And we want to ask is, what are our relatives? What are the galaxies that we actually did eat up in the past? What did they contribute? Where did their dark matter end up? And as we learn all of those questions, in that way we can actually build a map of the dark matter in the Milky Way. So with some of the new data that's been coming out, this process of reconstructing the Milky Way's family tree is actually becoming viable now. And we've been learning a lot. And what I'm going to show you over the next few slides is how we can actually build up a history going back almost 7 billion years at this point. And I'll tell you a little bit about what our old ancestors are, how big they were, when we ate them, and well, now they're gone, but what their effect is on the galaxy as we live and breathe in it today. So this process is essentially like going on a dinosaur hunt. So imagine a dinosaur archaeologist, right? You're going to go out, you're in the field, you find some fossil, and then based off of the shape of that fossil, or maybe the environment in which you found it, or maybe you do some radioactive dating, you can infer something about the creature that fossil came from, right? But you're taking hints from whatever's left behind and inferring something about the animal that lived there a long, long time ago. When I first showed this slide, one of my postdocs, I had a more traditional picture of a Tyrannosaurus rex, and one of my postdocs was like, no, Tyrannosaurus rex has feathers, so you can't show a picture of Tyrannosaurus rex without feathers, so he found me this one. And so I started including this one in my talks, and then 2 months later, he sends me an article that says, essentially, actually, Tyrannosaurus rex did not have feathers. There's a new updated study. But I think now that this is actually a really nice example of this inference process and where it can fail and where it actually succeeds. And so, we're doing the best we can with whatever little evidence we have to actually say something about that creature. And, we're making guesses, though, and those guesses will constantly be revised. So taking this analogy with dinosaurs to our own galaxy and the stars within it, what we want to do is essentially start off from a map of the stars in our galaxy, and then based off of that map, infer something about the history of how those stars got to where they are today. And the analogous properties that we use, like we're not going to use fossil shape or fossil environment or radioactive dating. What we're going to use in this case is the positions of the stars, their velocities, and perhaps the chemical properties of the stars themselves. But what I do want to emphasize is this is essentially like a rare event search. This is essentially harder, if maybe even, than going out and looking for dinosaur fossils, because the number of stars in this map here that actually would have originated from these kinds of events are subdominant to other stars that would have just been born in our galaxy. So you're really looking for very rare stars, some very small fraction of what's there. And then once you find those small, that small fraction, you want to use them to do this inference process here. So the reason why this our ability to reconstruct the Milky Way's family tree has suddenly received a big boost is essentially because of data from the Gaia satellite. So let me play this video here. So the Gaia satellite was launched in December of 2013. It's an ESA mission. It is orbiting fairly far from the actual location of the Earth. That's to try to prevent any temperature fluctuations from the Earth in terms of affecting the telescopes on the satellite. It has this solar shield, which you can see as the kind of like wings, circular wings. And let's see, here it is. It's at the L2 Lagrange point here. It completes a single orbit there in about 180 days. And in that process, it actually has 2 telescopes. So those 2 telescopes span the sky. And essentially what the telescopes are doing is just measuring the positions of the stars on a repeated basis. And in doing that, you can get really precise measurements of the motions of the stars. So the total number of stars that Gaia is going to eventually have complete data on is going to be about 1 billion stars. This is unprecedented. There's about 1% of all of the stars in the Milky Way, which might seem like a small number, but it's way more than we've ever had. And to have the full information about their positions and their velocities is revolutionary. So like when the Gaia data first came out about a year ago, they had the second data release. I went to this release party that was occurring in Manhattan. And so it was essentially a bunch of scientists, and we were like on 2 floors in this building and hacking away for 2 days. And it was just funny because everybody was super excited. I mean, you just feel like the energy in the room. And what were we doing for those 2 days? We were trying to figure out how to download like a file. There were errors and it wasn't working, but like nobody cared, right? It was just the fact that like that file that we were downloading was just so, it was like special, right? So to put this in a more historical context, this image here is actually showing, summarizing our ability of mapping stars since going back to all the way down to the time of Hipparchus. So on the top panel here, the blurriness around each star tells you, indicates the precision which we could measure its position. So you can see that this is 11th century BCE, and then moving here up to 1801, we got much better at measuring the actual positions of the stars, and we could do that for many more stars than we could in the time of Hipparchus. On the bottom panel here, the lines on each star indicate our ability to measure its distance to the sun. And the longer the line, the larger the measurement uncertainty in measuring that distance. So this here is work of Bessel and Henderson and Struve, so 1837 to 1840. So you can see not very many stars, and the errors on their distances were very large. And now as we move here into the 1900s, the number of stars that we can measure the distances for increases, and not only that, but the errors on those distances improve dramatically. And where you see some of the biggest jumps is going from here to here, and that's because these telescopes were all ground-based, and then this was the first satellite astrometry mission. And in going from the challenge associated with the ground-based telescopes is that there's atmospheric effects that prevents you from getting these distances really well. So when you send a satellite into space, you avoid any of those issues, and you just get much better improvement on that. So this is the Hipparchus mission, which flew in the early 1990s, and this is Gaia. So you can't even see the lines in Gaia anymore because the precision is actually so good that it's smaller than the size of the little star symbols in that plot. So that's really kind of underlying the vast improvement that we have now with Gaia. Not only are there more stars, but the uncertainties on all the measurements of the properties of those stars has gone down considerably from where we're at. And so all of those improvements taken together suddenly allow us now to start going out in the field and doing some of this archaeology to actually, turning it into a bit more of a precise science. So let me tell you a little bit about what we actually learn using this data. Let's backtrack. So here's our Milky Way today on our family tree. I'm going to only show you some highlights of our most interesting relatives, let's say. Let's call it that. So if we go back about 3 billion years, we get a very interesting relative. This relative is known as Sagittarius. Sagittarius is a small galaxy that we know is in the process of getting eaten up by the Milky Way today, but it hasn't gotten totally digested yet. I may be taking that analogy a little bit too far. But here's a movie of what this process would look like. So here's the original Sagittarius galaxy. Here's our Milky Way disk. And now that Sagittarius galaxy is falling in, and as it's getting eaten up, it's essentially getting completely shredded, and its stars get removed and essentially end up following the orbit of the galaxy as it fell in. So this is what we see today. We see the Sagittarius galaxy here. We see that it's being disrupted, and because we see it, we know it hasn't gotten completely digested yet. But we also see all of these stars forming these loops. And based off of those loops, we can actually learn something about how that galaxy has fallen in. It actually allows us to retrace the steps of the galaxy in the process of it being eaten up, which is pretty spectacular. So, everybody ready with your colors? Yeah, good. All right, so for this particular example of the Sagittarius galaxy falling in, we have some star from that Sagittarius galaxy that's gotten removed. What is the probability, do you think, that that star will actually hit a star that's in the Milky Way? Negligible, 10 to 30%, 50 to 75, or greater than 80? Interesting, yes. So it seems like there's a dominant opinion that we should fall in this set of colors, red or green. And indeed, the probability is very low. It's essentially just negligible, but very, very low. And the reason for that is that the stars in the Milky Way are actually so spread out that most of the times when Sagittarius is passing through anything, it's essentially passing through nothing, right? And so the likelihood that it hits a Milky Way star is very small. So what is Gaia expected to do to this picture? Well, I showed you an example of this stream of stars that's formed from Sagittarius. That's perhaps the most spectacular example we have of a stream in our galaxy, which is why I wanted to start off by showing you that one. But there are many more. And indeed, this is an image from the Sloan Digital Sky Survey that is referred to as the field of streams. Because in this image, if you, it might be a little hard to see, but if you squint, there's actually a lot of structure here. So here's Sagittarius, this bright swath kind of cutting across here. But there's several other streams. So here's, this one's called Palomar 5. This one up here is called GD1. Here's Orphan. Here. So it's kind of like the sky is actually crisscrossed by all of these streams, where these streams are relics of objects that have fallen in and have gotten, are either in the process of getting completely disrupted or have totally been destroyed. And so one place where Gaia is expected to have a really huge effect is in improving the mapping of these streams. So this is old data that I'm showing you here. The expectation is that this map is just going to become even more beautiful. We're going to see even more structure that's there. So let me tell you a little bit, actually, of one of the first results that has gotten people really excited, having to do with streams in the Gaia data. So in particular, we're going to focus on this stream here now, GD1. Oops. This one here. And this particular stream is located maybe about twice the distance of the sun from the center of the galaxy. It's a very long stream and one that's been studied a lot over the years. But it's the precision with which we can study GD1 has improved greatly. So here's the image with previous Sloan data. You can kind of barely even see it. And here's what we see now with the Gaia data. There's the stream right there. So now you can actually just see it without even squinting. And we can do things like, so people have do analyses where they subtract out backgrounds and they can look to see what are the stars that are actually, for sure part of that stream. And what you see is this black section, as you see all these bumps and these wiggles, and there's regions where it looks like there might even be like breaks in the stream. So there's actually a tremendous amount of structure that's there. And this structure, we hope, might actually tell us something about dark matter that's flying around in our galaxy. Why is that? Well, let's take this picture here where we have a stream. And now imagine that there's a clump of dark matter. So some gravitationally bound dark matter structure. It has no stars in it. It's completely dark to us. So there's no hope that we'd ever actually be able to see this thing by eye. But it's flying around. If that dark matter subhalo or clump flies through one of these streams, it'll perturb it, because the stars in the stream are going to feel its gravitational effects. And in particular, in certain cases, it can actually just break the stream in half. So what we can do is go out and actually look for these perturbations in the stream and look for these breaks. And if we find them, then that would actually tell us something about whether or not the dark matter is clumped in this way and distributed like that in the galaxy. So there's a very exciting piece of work that was put out last year in 2018 by these groups here, analyzing the GD1 stream in greater detail. This is with data from Gaia, and looking in particular at these perturbations and the breaks in these streams. So here's, this is the data up here. So you see something here that looks like there could be a break. There's another position here where it also looks like there could be a break, and there's kind of something coming out of it. The bottom is a simulation, so a model of what that stream would look like if it was being perturbed by dark matter clumps. And what's pretty stunning is that a lot of those features you can reconstruct. And so it's still early stages, so there's still a lot of additional tests that need to be done. But suffice to say that these initial results with the new Gaia data have gotten people really, really excited, because it might provide the first ever evidence that there's these kinds of dark clumps, these dark subhalos flying around in the Milky Way galaxy. And it would be a very direct way of mapping that kind of structure in the Milky Way. And let me conclude now with our last relative that we are going to discuss. So we talked a little bit here about Sagittarius, where we see these streams and we see what we can learn about dark matter using these streams. Now we're going to go even further back in time. So now we're going to go about 7 billion years back in time. And here, there's actually, with the Gaia data last year, there was the first indication. We finally pinned down, this would be our oldest relative, so our oldest grandparent or great-grandparent or whatever we want to call it. And this galaxy was probably quite large. It was maybe like 10 to the 7, 10 to the 8 times the mass of the sun today. And what we believe happened is that it fell into the Milky Way, and in falling in, got completely disrupted. It donated all of its stars to the inner part of our galaxy, and the vast majority of the stars in the inner part of our galaxy are actually from this relative. So we're essentially living in the midst of all of the stuff that was donated by this old relative. And one of the things that my group has been studying is what the implications are of this for dark matter, because if most of the stuff in the inner parts of our galaxy have been donated by one single relative, that relative would also have donated dark matter. So what we've been looking at is whether or not the fact that you have these kinds of, the fact that this merger existed can actually be used to infer things about how fast the dark matter has been going. In particular, what we find is that for the kinds of mergers, such as this old galaxy, the dark matter and the stars that it leaves behind in our Milky Way act essentially very similarly. So if we go out and we actually measure the velocities of the stars that we believe came from this relative, that is actually a direct speedometer, in some sense, for the dark matter that would have also come from this galaxy. So we can use those stars as a direct tracer for what the dark matter is doing. So these are ideas that we can go out and we can test in simulations. And then in simulations, we can understand what this correlation is, and then we go out in the data and we actually measure the velocities of the stars. And once we do that, then that actually tells us something about how the dark matter itself should also be acting. That completes our brief tour of the family tree that we'll go through tonight. I really wanted to emphasize these two examples. So we have the example of objects and mergers that give us streams, and then we also have this new discovery now of our oldest relative, and that's just come again from this data from just last year. So all of this is very much current work and ongoing. So what all of this taken together allows us to do as we complete this family tree and continue growing it, is it allows us to build a much more sophisticated map of the dark matter that's in the Milky Way. So we started off this evening with this very simple picture, right, where we had this big halo and our galaxy is in the middle and there's essentially no structure that's there. But with the data from Gaia and everything that we've been learning, we're moving towards a picture that's much more stunning in many ways, much more complicated. So we can now, we're hoping, possibly be able to reconstruct these subhalos, these dark some dark matter clumps. We're also hoping that we can do things like reconstruct the speeds of the dark matter that are moving around in the galaxy. And once we continue building that map and finalizing it, then that's the important input that we can now take that back and make predictions for experiments, because it's that map that dictates the dark matter that flies by Earth, that dictates the rates of the dark matter particles as they hit nuclei in the detector, and potentially tells us how many of these events we should end up seeing in our experimental labs here on Earth. So the hope in this whole program, taking both the experimental program, the terrestrial experimental program, and coupling it with what we're learning from astronomy, is that we will ultimately end up being able to actually identify the particle that the dark matter is, or whether or not it's more than one particle. Here on the left is all of the known fundamental particles that we have discovered so far. What we're hoping to be able to do with this program is to add on the additional dark matter particles and have some idea of what they actually are, what their masses are, how they interact with everything else. That's the ultimate goal. What I'm often asked is, how long do you think it's going to take? And I don't know. And actually, I find it kind of interesting to go back and look historically at all of the particles we actually have discovered, the amount of time between prediction to discovery. So this is a list of all of those particles. And each little bar here tells you that this initial part of the bar tells you when that particle was predicted, and then the final is when it was discovered. So you can see a couple remarkable things. So here's the electron, right? So that was the first one. The 1960s was a very productive time in particle physics, so many new particles discovered one after the other. The Higgs was the most recently discovered, but also the one that took the longest from the time at which it was first predicted. And in some sense, I think the dark matter particle is going to be the hardest, even amongst all of these, because we know so far less about it. We have very little idea. The mass range it can take can span many orders of magnitude. The kinds of experiments that you would build to look for dark matter can vary accordingly. And so there are, the challenges there are really quite commensurate, especially relative to what we've already seen. But what I find particularly exciting about this field of research is that it really demands, because the problem is as hard as it is, it really demands crosstalk between so many fields. So, I mean, just over the course of the last hour, we've gone from, the most fundamental of levels, talking about quarks and the Higgs boson and dark matter interacting with nuclei in that way, to also talking about scales so much bigger than that, scales where we're looking at motions of stars in our galaxy and understanding how our galaxy grew. And it's only by taking information on all of those scales and bringing it together do we really have a hope at really being able to make more precise predictions and really kind of getting at what actually the dark matter is. So with the kinds of data that we're coming in now, I think I'm very hopeful that we'll start getting some hard clues that we can latch onto and start deciphering in the next few years. So we're just going to have to see how that all ends up playing out. So I think it's a very exciting time given the data that we currently have on the table. So with that, I will conclude. Thank you very much.
So we have time for some questions, and the procedure for questions is rigid. There are people with microphones, and they will come to you when they spot you with your hand up, so you have to kind of be persistent. When you get a microphone, it's going to have a color, piece of foam on top, and I will call on you by that color. When I do, please stand. This is simple. Stand. Tell us your name. Tell us whether you're a member. The really hard part is ask a question. Just ask a question. So we'll start with the red microphone, and then we'll go to blue over here.
Elisa Wynn, I'm a guest of a member. When you're talking about a detector, your deep, isolated detectors, how do you intend to differentiate from neutrinos? Is it a matter of velocity or what?
Yeah, it's a
Thank
great
you.
question. So it's the neutrino signal is actually going to be weaker than the dark matter signal. So it depends a bit on what the dark matter model is. I should use that as a caveat. So far, the kinds of models that the experiments have been able to probe, the dark matter signal is stronger than the neutrino signal. And so we've just been able to ignore the neutrino backgrounds. Now, what's really interesting is that the experimentalists are so darn good, and these experiments are getting so sensitive that they are probably in the next 5 or so years hitting into a region where the neutrinos are going to become the dominant signal. And so now, for the first time, these experiments are going to go from being zero background to having a coherent neutrino background. And everybody's actually in the community just kind of stunned in terms of the fact that we've even reached this point that these experiments are so good that we can even see this neutrino signal. But it is going to be an additional challenge now to searching for dark matter, because there's going to be something else going on in that detector that will kind of be mimicking that signal.
Blue?
My name is Al Ehrlich. I am a member. Can you tell me roughly how many orders of magnitude difference there is in the cross-section for interaction between a dark matter particle and a neutrino?
Okay, so it depends, again, on the model. But so if we run with the picture of the dark matter scattering via the Higgs boson with the nucleus, if the dark matter is larger in mass than about 50 GeV, or 50 times the mass of the proton, then it's several orders of magnitude stronger than a neutrino signal. Oh. If the dark matter is less massive than that, it actually can be comparable.
And very quickly, when was the dark matter particle first predicted, so I could put it on that graph?
Oh, yes, interesting. So yeah, okay, so let's go back to the graph. Well, one can argue it's Fritz Zwicky in the 1930s. So he had a paper measuring the velocity dispersion in the coma cluster, of galaxies in the coma cluster, and he sort of had a very offhanded comment at the end of his paper. It's actually really interesting. I've gone back and pulled up this paper. It's all written in German, but at the end he has like this very offhanded comment that's like, well, there's something here in the data that doesn't make any sense. We'll just call it dark matter. But I don't even think he took it very seriously, right? It was just a really kind of throwaway comment, probably just to get the paper published. And so, okay, so maybe we could say the 1930s, if we want to go with that. If we want maybe a more rigorous time, it maybe was around the time of Vera Rubin's measurement of the rotation curves, because then that was starting to be floated around as a potential idea. So maybe like 1970s. Yeah.
We have a black microphone back there, and then a red one, and then we'll do a blue one.
Yeah.
Black, red, blue.
My name's Joseph Powers, and I'm not a member. Besides Gaia, there's a lot of extremely large ground-based telescopes. So I wonder, what do you expect to get from LSST and some of like the 30-meter class optical telescopes and those coming online?
That's a great question. So LSST is will be getting essentially a measurement of stars that are much fainter than Gaia, so being able to map out a bit further out in the galaxy. So one place where LSST is going to be particularly powerful is actually coming back here to our measurement of breaks and streams. So LSST is going to greatly improve our sensitivity to structures like this inside the stream. That's one example. It should also end up improving our ability to reconstruct other relatives in this process, probably other relatives that are still kind of living like further off in the outskirts of the galaxy. Also potentially discovering new dwarf galaxies that are orbiting ours. So there's a lot of science that can be done with LSST, and actually there's a growing community of physicists that's starting to work on a lot of these ideas to develop the dark matter program for LSST.
For those of you interested in LSST, there was a PSW talk on that by the director, and it's posted on our YouTube website. Red microphone.
My name is Scott Matthews. I'm not a member. How can you say with certainty that the dark matter particle is not a particle that's already in the standard model? And in particular, I'm referring to neutrinos, especially in light of the fact that the neutrino may be Majorana, there may be sterile neutrinos, there may be relic neutrinos. How do you rule them out as the dark matter particle?
Yeah, great question. So let's go back to our standard model here. Where is it? Here we go. So, right, so if we look at all of the particles we currently know about, there are 3 neutrinos there, the electron, muon, and tau neutrinos here. So with the neutrinos, there's a lot we don't know about them. Like we only have bounds on their mass. We don't know their exact mass. They have some very unusual properties. So they like oscillated mass, and there's really just a whole program of study for these neutrinos. So yeah, why can't they just be the dark matter? They're neutral and they're very weakly interacting. We can calculate how many of these neutrinos should be present, like what their abundance is today in the universe. So like what fraction of the particles flying around in this room are neutrinos. And that fraction is a lot smaller than the total amount of dark matter that we know is there based off of cosmological measurements. So in particular, the CMB. So specifically, neutrinos are about 3 or 4% of the total amount of dark matter. So they are a form of that dark matter, but they're going to be a very, very small fraction. If we extend the standard model by adding additional neutrinos, so this is the sterile neutrino that you've talked about, it is possible that the sterile neutrino could be the dark matter candidate, but we haven't actually discovered the sterile neutrino. And that would be an extension because it wouldn't be one of the neutrinos that's already in that diagram.
We have 2 blues up here.
Okay. Colin Albertson, I am a member. I want to swing it back from particles back to galactic archaeology here for a second. When I was a kid, it just seemed to be assumed that the Milky Way was just a regular old spiral, but it seems to be like the last 20 years or maybe a little bit more, I guess the realization has sort of set in that it's not, it's a barred spiral. And my question is there any sort of speculation as to whether or not dark matter is determinative of what the basic structure of a galaxy is? And when you're talking about the family tree of the Milky Way, was there a point at which it wasn't a barred spiral, and could it not be in the far future?
Yeah, so a lot of details about how the galaxy itself evolves, like just the stellar part of the galaxy, is also very much open question, and it's becoming a lot better now because the simulations, like I showed that movie of the simulation, like those are actually becoming so much better now that we're reconstructing galaxies that actually start looking like a Milky Way galaxy. They've got bars, they've got spirals, and so with the improvements that we're getting from simulation, we're actually going to be able to start answering those kinds of questions in a lot better detail than we can now. I don't think it's whether or not the presence of the dark matter affects the formation of those structures is not very well understood. Probably if the dark matter is sort of the simplest kinds of models, my guess is it probably wouldn't affect it very much. But it could be that in some more complicated models where the dark matter can interact with itself or cool, it could form structures that could potentially affect it. And I don't think it's well understood how.
Blue microphone, please stand up, tell us your name. Yeah, you have the microphone.
Okay.
You're on.
I'm not a member. My name is Ty Avni, and my question is: does dark energy have the same impact on dark matter as it does on, visible matter? And then the second part is dark matter increasing as dark energy as the universe is expanding?
Oh, okay. So what dark energy does is it causes it's causing things to expand. It's causing the acceleration of the universe, and so essentially its effect is going to be most observable on large scales, whereas dark matter is forming these highly concentrated clumps of matter on smaller scales. So the scales on which they're having the greatest impact are different. And what was the second part of your question?
The second part of the question is dark matter also increasing? Energy is increasing as the universe is
So the second question was whether or not the dark matter abundance is increasing as a function of time, essentially. Yeah, so we believe that it doesn't, that it's essentially the dark matter abundance is constant today. So it sort of changed in the early universe, and then as the universe was expanding, but essentially has reached an equilibrium point, so its abundance is staying relatively constant.
Don't have a conversation because you don't have the mic. And if you don't have the mic, you won't show up on the video. So save it for the social hour. Thank you. We're going to have a question from the red mic there. Then we'll have one from the blue mic. And if somebody can get a microphone to David Rosen, I think he has a question back there. So if you can get him the black mic maybe. So let's start with the red one.
Okay, we have an online question from the live stream. This is from Joel Wilson. He's a member of the Society. And he's asking, do we see any impact that the dark matter clumps have on predictions made by general relativity?
You mean in terms of detections with LIGO?
So he says, for example, the recent imaging of supermassive black holes, would we expect to see any clumps near galactic cores, which is where the supermassive black holes reside?
Oh, yes. So where the dark matter density is going to be strongest or largest in the galaxy is going to be near the center, which is also where the black hole is. And so there are some ideas about maybe the dark matter also getting caught and giving you sort of, because of the presence of the black hole, it might end up giving you density spikes in the dark matter very close to the center. That's one hypothesis. A separate hypothesis is these black holes are so powerful that they're essentially injecting energy near the center of the galaxy, and it blows the dark matter out. And so instead of giving you a dark matter spike, it actually gives you a dark matter core. And I think at the moment the verdict is out as to what's actually happening. Like, again, this is one of these cases where we have to rely pretty heavily on the simulations. And the simulations have been starting to get good enough now that we can start making some predictions, but it's still a bit of an open question.
We're going to take David Rosen's question, and then we'll have the blue microphone. And then if the blue microphone can teleport over here to Carl Merrill, we'll take Carl's question. Okay.
David Rosen, lifetime member. If the signal from the dark matter is larger than the neutrino background, and we've measured a good part of the neutrino background, how come we haven't already detected the dark matter?
Oh, so we haven't actually measured that neutrino background yet. We're at a point where almost having the sensitivity to really be able to hit it. Yeah, so that's why we have it, because the dark matter models that we've been able to exclude up until now predict, have rates that are larger than you'd expect for the neutrino background. But in the next few years, the experiments are going to be hitting that point where that neutrino background is going to be comparable in size to the dark matter signal.
Slight modification. We're going to go to the black microphone, and then we'll go to the blue microphone.
Hi, my name is Ben. My question is, I'm not a member, sorry. My question is, so Gaia is mapping 1 billion visible stars, right? As I understand it, even among the matter that we know about now, non-luminous matter makes up at least a sizable, maybe even a majority of the matter that isn't dark matter. How, when you're mapping the history of our galaxy, for example, are you taking into account the effect of the interstellar or intergalactic media?
Yeah, so for the kinds of results that I was showing you, we're pretty much only looking at the stars because they're easier to trace and detect, and you can actually see all these interesting structures in them. The majority of the gas that's in the Milky Way is in the disk, and was essentially it's in the disk it's in the disk of the Milky Way. And what I've been talking about in terms of being able to reconstruct the history, most of what you're looking for there are things that got dragged in and are kind of off of the disk. And so looking at like the disrupted gas or something like that from that satellite's a lot harder than looking for like these structures in the stars on the distances and where you're seeing them. It's very different than like looking at gas that's in the disk of the Milky Way, because that's kind of concentrated in a small spatial region.
So I think I have a question with the blue microphone. If somebody could bring a microphone up here to the front to Carl, that would be good.
Adam Malloy, I'm a member. Can you describe the dark matter clumping that occurs? And is it predicted? What predicts that?
Yeah, so it's actually it's a very natural prediction for these dark matter models. So what happens is you start off with, imagine if you have any kind of small amount of matter perturbations in the early universe, each of those is going to end up growing with time. And so you end up having a distribution of clumps, essentially, in this process. So some of those initial matter perturbations are going to grow really large to give galaxies like like our Milky Way and really large galaxies. Some of those perturbations are just going to grow a small amount, and they're just going to give you little, sort of smaller clumps. And you can think of a smaller clump as being like the thing that would eventually grow to be a really big galaxy. It just hasn't quite gotten to that point yet. And it's so small that it has no visible matter in it. So the standard cold dark matter picture, so where the dark matter is non-relativistic, which is essentially the framework I was working under in this talk, actually predicts that you should have a ton of these small dark matter clumps going all the way down in mass to about Earth scale size. And so these should be like peppering the halo. There should be a ton of these just kind of flying around. And a detection of one of those would actually be a very concrete, it would concretely be a piece of evidence towards this cold dark matter picture.
Carl.
Carl Merrill, member of the Society. I have a question, but it's actually has to do with energy or levels of dark matter. In the extreme, could dark matter form a star or a star-like structure? That's number one. Number two, in the same vein, could it interact with massive stars? And in the final part of that same question is, could, if we went through a clump, could it perturb the solar system?
Ooh, so many parts to that. That's all, each one of those is like a whole separate conversation, which is great. So everything I'm going to say is, of course, it depends on the particulars of the dark matter model, which is almost always the case. But yes, in certain models, the dark matters can form stars. There would be dark stars. There's theorists have been working on that. In other models, the dark matter can get caught by stars. So, for example, the dark matter can get caught by the sun. And then maybe it can annihilate inside the sun and give us some really interesting signal from the sun. So people have studied that. And now I don't remember what the third one was.
Could it perturb the solar system?
Oh, could it perturb the solar system? It's very likely that the density of these things flying around the solar system is too small to actually cause a noticeable perturbation on the orbits of the planets around the solar system.
Who else has a microphone? Okay, we have a black microphone there, a blue one? Somebody have one? A red one, okay. You have to get the microphone to people who raise their hands.
My name is Rachel Simcoe, I'm not a member. To drag the conversation back to neutrinos, because I actually want to hear about the dark star, but what are the differences between the experiments that you're using to identify dark matter and neutrinos, or are they the same experiment?
Good. See, so it depends on what you want to test for the neutrinos. So the experiments that I was talking about here that are built as dark matter experiments will sort of naturally end up giving you some amount of neutrino scattering at some point, which is what people will end up seeing in the next few years, as we were discussing. That's looking in particular at what's called coherent neutrino scattering, where the neutrinos are scattering off of nuclei and you can measure those rates. What you won't end up learning from those experiments is really details about what the neutrino mass is, properties about. There's a lot of questions about it. We don't know if it's Majorana or drag. I won't go into the details, but let's just say that there's a whole list of questions about neutrinos that we just don't understand, and that we're not going to be able to get from these kinds of experiments. You need very dedicated sets of experiments to look for those, and there's a big wide-ranging program on that.
I'm James Griffin, and I'm a member. I have two brief questions. With the map, the nuanced map you had of the dark matter, does one expect the peaks in the dark matter density to correlate in some way with visible matter peaks or not?
So in this picture...
The other question is, do we ever have a chance from the archaeological approach of finding out the mass of a dark matter particle, if there is one?
Ooh, okay, yes. So let's do the first one, which is here. So these you're referring to like if this is the dark matter map, right, schematic, right, and these were the clumps I was telling you about. Most of those clumps are going to be so small they wouldn't actually contain any stars or gas. The biggest ones of those will contain little galaxies. So in the picture I showed earlier, where it was all of the galaxies we currently know of. So essentially we have seen some of these clumps, just the really big ones that have galaxies in them. Here we go. So like these small dwarf galaxies are essentially the big clumps of dark matter that would have galaxies inside of them. But we also expect that there's going to be ones that are much smaller, so that don't have any galaxies at all. Now, whether or not we can actually learn about fundamental physics, the fundamental properties of the dark matter doing this exercise with this archaeological program in some sense, I'm hoping that there are certain questions that we can answer using data from Gaia. It's ongoing work that like my group and many other groups are working on. But the hope is you might be able to answer questions about whether or not the dark matter can interact with itself, or whether or not it can cool and lose energy and form interesting new structures. And all of that would really be kind of probing the fundamental particle physics of the dark matter. So that's all kind of ongoing work, but there is hope that you could also be able to use this data to test that directly.
Black, then blue. You're black. Please go.
I'm Arthur Malella. I'm a guest of a member here today. Other evidence for dark matter, besides the motions of the stars. I think I read that there's gravitational lensing that you get with it. Is that correct?
Yeah. So there's a variety of different pieces of evidence, and actually one of the things that's so stunning about it is that the pieces of evidence scan a whole array of scales. So what we talked about was the evidence coming from galactic motions. So that's maybe perhaps on the smallest scales. On the largest scales, from the cosmic microwave background, that actually provides us with, when we say that there's 85% of the matter is dark matter, that 85% is coming from CMB measurements. So we get precise measurements of the quantity of dark matter from CMB. On sort of middle scales is motions of galaxy clusters. So one spectacular image, which I guess now I wish I had because I could show you, but if you have two clusters of galaxies and they collide with each other and pass through, the dark matter that's surrounding those clusters doesn't interact very much, so it just kind of flies through. And all of the hot gas gets caught in the middle, because that does strongly interact. And we can see these systems. So we can see systems where there's hot gas emitting X-rays in the center, and then using using gravitational lensing, we can infer the fact that there's a lot of mass on the outskirts that's the dark matter that flew through. If you want to see this image when you go back home before going to sleep tonight, you would want to Google bullet cluster. It's a really spectacular image, and it's essentially a picture of these galaxy clusters after they've passed through, and we're now able to reconstruct where the dark matter is and where the gas ends up.
Blue? And black.
Hello, I'm Lorenzo. I'm not a member. Could dark matter be many-body states rather than elementary particle? And could you distinguish between the two cases experimentally?
Yeah. So one of the things that I think is really interesting is that for the last 20 or 30 years, there's been a single paradigm that's really been dominating our view of dark matter, and that's the fact that we assume it's a single particle and it interacts very weakly. Over the last few years, the theory community has really been going through this phase shift towards a much more complex picture of what the dark matter could be. Like my own thinking on this is sort of, well, if 15% of the matter is the stuff we see, and we know that that's super complicated, why are we assuming that the other 85%, which is the stuff that we don't see, is a single particle and in some sense very, very clean, right? Like, why isn't it just as complicated as everything else that we can see? And so there's a shift now, I think, in the community that's starting to think about these types of scenarios where you can have the dark matter form perhaps like atomic dark states. Maybe those atomic dark states can interact with each other. Maybe they can cool in interesting ways. Maybe they talk or maybe they don't talk to the visible matter. It does open up a whole set of new possibilities, but perhaps it's maybe a more realistic scenario. It certainly motivates a broader search program, and the community has been moving towards sort of diversifying the kinds of experiments that are currently being done so that we can catch these types of scenarios.
So we're going to take 2 more questions. We're going to have this red microphone here first, and then the black one will be the last question.
I'm Dennis Miller, a member. I'm curious, you said that the universe, or excuse me, the galaxy is surrounded by dark matter, and it's in a certain shape. Is that shape controlled by some gravitational force defined by, say, the theory of relativity or some other measure? And then secondly, when Sagittarius came through into the galaxy, was there any disruption in terms of gravitational waves or any disturbance caused by the black hole that is in Sagittarius? And then what happened to that black hole once it entered into our galaxy?
So I'm actually not sure if Sagittarius itself had a black hole. But with that caveat, let's assume it did. It would just be sort of flying around. It gets eaten. Sagittarius is donating everything, and along with it, donating its dark matter, it's donating its stars. If it has this black hole, it would donate it as well. There would be no measurable gravitational waves from this kind of interaction. It'd be way too weak to see anything. Like the kinds of gravitational wave signatures that, let's say, LIGO is picking up are from extraordinarily violent collisions between black holes. And so you wouldn't see any of these kinds of gravitational perturbations from Sagittarius falling in.
Last question.
Yes, hi, I'm Rich Esposito.
Can you hold that closer to your mouth?
I'm non-member so far, so, okay. Yes, so is there an imbalance between in the strength of how the dark matter affects light matter and how light matter affects dark matter?
Do you mean does the strength of interaction vary in those?
Yes, well, I've heard a lot about how dark matter will affect what we see, the light matter. But do we know how much light matter affects dark matter?
One way in which it can affect it is, well, let me take a step back. I think the answer is no, we don't know very much. We have guesses as to ways in which it potentially can. So one example is if you have like supernovas that burst and explode in the Milky Way disk. Those explosions are so energetic, they tend to distribute and power the dark matter out, so they push the dark matter away. Same thing with the black holes in the center of the galaxy. So that would be one example where certain features of our own galaxy that we can see, like these kinds of interactions, supernova bursts or the presence of the black holes, are actually causing the redistribution of the dark matter in the halo. So those would be 2 examples that I can think of for that.
Okay, well, thank you so much. Well, I'll have to do this at a distance, I guess. Unless you turn down the volume on the...
Well, I turned mine off, so.
Oh, okay. So in appreciation for your coming here and spending time with us and giving this very interesting lecture on dark matter, I have a frame copy of the announcement of your talk as a present, signed by all the members of the General Committee on behalf of the membership, and also a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington.
Thank you.
As described earlier. So thank you so much.
You.
Before we go, there are the usual closing announcements and housekeeping items. PSW depends on members and sponsors. If you're not a member, please consider joining. If you are a member and you haven't paid your dues, shame on you. Please pay your dues immediately. If you paid your dues, consider giving an additional donation, sponsoring a lecture or a series, and volunteering to help carry out the Society's activities. We're all volunteers. There are no paid employees. You can apply for membership and make contributions via the PSW website. It's really pretty easy. You just go to the Join button on the home page, which will pull up this form about joining. And if you push on this link, you'll get that application. If you'll fill out all of the places that have a red asterisk, indicating that those are required fields, and provide any additional information you like, you'll eventually get down to the bottom, and you press the Submit Form button. It will bring up a dues payment button. You have to pay, I'm sorry to say, but you do have to pay. And your membership application will be forwarded to the committee and considered, and you'll hear about whether you've been elected to membership or not in pretty short order, maybe a week, 10 days. The only requirement for membership is a genuine interest in science. There is no IQ test, or any other test for that matter. So please feel free to apply. Please see Corresponding Secretary Robin Taylor. It's at the back of the room if you have any questions regarding membership, because our membership director, Lloyd Mitchell, isn't here today. It is worth noting that PSW lecture attendance, this is a little bit unusual, but we average over 100 in person and about 30 on the live stream, which for the live stream are kind of modest numbers compared to Kim Kardashian. But PSW videos have been viewed over 250,000 times on the PSW YouTube channel, and over 8 million minutes of cumulative watch time, which means that one person would have to sit and watch the videos for 24 hours a day, 7 days a week, 365 days a year for about 1 year and 6 months. The point being that PSW activities reach a growing worldwide audience, and dues contributions and sponsorships make this possible. PSW is a nonprofit educational organization. It's tax exempt under Section 501c3 of the Internal Revenue Code. Contributions are tax deductible to the extent permitted by law and by the IRS. All PSW members in good standing are entitled to wear the PSW rosette. If you want to purchase one, they're $15, and you may do so online or at the rosette table in the back. Where are we? Our next lecture will be by Kim Janda of the Scripps Research Institute, and he'll be speaking on vaccines to combat the opioid epidemic. Promises to be a very interesting lecture. And thereafter, we have a special event only 3 days later, so I urge all of you to come. Don't be exhausted by the fact that you have to see 2 PSW events in 3 days. Alan Stern, who was the principal investigator on New Horizons that brought back such spectacular results from getting all the way to Pluto and ultimate Thule, and is now traveling into the Kuiper Belt, will be discussing and debating with Ron Eckers, who is the past president of the International Astronomical Union, the question of what is the proper definition for the word planet. As it turns out, there had not been a definition of the word planet prior to the meeting of the IAU to establish a new meaning, which had the consequence that the Elite Eight remained the Elite Eight, but number 9 was expelled and is no longer considered a planet. And then on May 17th, we have the 88th Joseph Henry Lecture, and our speaker will be Brian Keating. His talk will be on the Big Bang and inflation, glimpsing the beginning of time from the ends of the earth. Brian was the PI on BICEP 1, and he's the PI on BICEP 2, and he is the director of the Simons Observatory. He searches for anisotropies in the cosmic microwave background radiation. He was He is also the author of the popular book, Losing the Nobel Prize, in which he recounts how the BICEP 1 team was a bit too enthusiastic in interpreting their data and thought they had seen predicted anisotropy that turned out to be due to cosmic dust. But he is very charismatic, and that promises to be a very interesting and enjoyable evening. So I urge you all to come. With that, I will note that the social hour ends at 10:30 promptly. Please use the side entrance to exit the building. And I will now accept a motion for adjournment of the 2,407th meeting of the Society to the social hour. And I have a, you always give the motion. I should just record you. I don't think that's permitted. I don't have a second. Second. All members in favor? Aye. All members opposed? The meeting is adjourned to the social hour.